Thank you, Mr. Chairman, and thank you to our witnesses. And let's say, I guess I'll start with some hometown cheerleading for Argonne National Lab, which, I find it quite remarkable. Argonne Lab has been, they've come out to events that we've had in my district dealing with the opioid crisis. And I find it incredible that at one single laboratory, we have everything from using the advanced photon source and its upgrades to directly image what are called G-coupled protein receptors at the very heart of the chemical interaction with the brain, all the way up through modeling the high-level function of the brain, the connectome, and everything in between. And it's really one of the magic things that happen at Argonne and at all of the, particularly the multi-purpose laboratories, which are really gems of our country. Now, one thing I'd like to talk about, and relates to big data and superconducting, is that you have to make a bunch of technological bets in a situation where the technology is changing really, really rapidly. For example, you have the choice of, for the data pipes, you can do conventional, very wide floating point things for partial differential equations and equations of state, things like that, the way supercomputing has been done for years, and yet there's a lot of movement for artificial intelligence toward much narrower data paths, 8 bits or even less, or 1 bit if you're talking about simulating the brain firing or not. You have questions on the storage where you can have, classically, we have huge external data sets, like the full geometry of the brain that you will then use supercomputing to extract the connectome. Now we're seeing more and more internally generated data sets, like these are games playing each other, where you just generate the data, throw it away, you don't care about storage at all. Or simulation of billions of miles of driving, where that data never has to be stored at all. And so that really affects the high-level design of these machines. In Congress, we have to commit to projects, on a sort of 5-year time cycle, when every 6 months there are new disruptive things. We have to decide, are these largely going to be front ends to quantum computing or not? All right, and so how do you deal with that sort of, internally in your planning? And should we move more toward the commercial model of move fast, take risks, and break things? Or do we have, are our projects that we have to approve in Congress things that have to have no chance of failing? And do you think Congress is too far on one side or the other of that trade-off?
I guess as a computer scientist, maybe I'll start here, and I would say that you've asked a very good question. I think this issue of risk and technology is very important, and we do need to take lots of risks and try a lot of things, especially right now, as not only are processors not getting in faster because of the end of Dennard scaling, but we're facing the end of Moore's law, which is the end of transistors getting denser on a chip. We really need to try a number of different things, including quantum, neuromorphic computing, and others. The issue of even the design of computers, if we look at the exascale computing program, with very important, of course, the first machine targeted for Argonne National Labs in 2021. And the process that is really fundamental to the Exascale project is this idea of co-design that is bringing together people who understand the applications, like Tony, and with the people that understand the applied mathematics, with people that understand the computer architecture design. And it is, the Exascale program is looking at both applying machine learning algorithms for things like the cancer initiative, as well as the microbiome, where you also have these very tiny data types, only 4 characters that you can store in maybe 2 bits, and putting all of that together. So those machines are being co-designed to try to understand all those different applications and work well on the traditional high-performance simulation applications, as well as some of these new data analysis problems. To answer your question directly, I think that, if anything, that project is very focused on that goal of 2021, and some other machines will come after that in 22 and 23, and the application. So it's not just about delivering the machines, it's about delivering 25 applications that are all being developed at the same time to run on those machines. It is a very exciting project. I actually lead the microbiome project in Exascale, and I think it's a great amount of fun, but it is a project that doesn't have much room for risk or basic research. And so I do think it's very important to rebuild the fundamental research program, for example, in the Department of Energy, to make sure that 10 years from now, we could have some other kind of future program that we would have the people that are trained in order to answer those basic questions and figure out how to build another computing device of some kind.
Well, yeah, thank you. That was a very comprehensive answer. But if you could just, in my last 1 second here, just sort of, do you think Congress is being too risk averse in our expectations, or should we be more risk tolerant that allow you occasionally to fail because you made a technological bet that is that has not come through?
I think I'll answer that from the science perspective. As a scientist, I absolutely want to be able to take risks and I want to be able to fail. I think the congressional question I will leave to you to debate.
Thank you. Yield back.
Thank you. The gentleman from California, Mr. Rohrbacher, is recognized.
Thank you very much, Mr. Chairman. I want to get down to some basics here. This is for the whole panel. Who's